some ways of characterize it. And then we will go to multifractals and also some ways of characterizing. Then, even if fractals were like recognized since very long time ago, until 80s were made like the definition that we use right now, and it's still open. Mandelbrot, and it's very similar to what is here now. So a fractal are patterns in a space that are similar in some way at different scales. So a fractal is a very mathematical thing. Then let's start like with the intuitive point of view of this. Then let's imagine we are walking by the coast of United Kingdom, and you're a very, very big person. Then your steps are big. What you see around will be like certain rocks formations, rivers, and as you walk with the smaller steps, you will see similar things. So in a real fractal, you can just study this self-similarity for a range of sizes. You cannot go infinitely small. While for an ideal fractal, you need to go to infinite small repetitive structures. Then some characteristics of a fractal. A fractal doesn't have a characteristic name. And what is this? So, for example, for a circle and for a sphere, the characteristic length could be the radius that tells us how to calculate it. Or for a cube, for a square, the length. Other example, more quite different. For an Ising model with a spin flip, in an equilibrium, some characteristic length could be the average domain sizes of spins. So why a fractal cannot have it? Because as you see different the repetitive structure of even more smaller scales, then you never can define this characteristic length scale. Also, a fractal is not differentiable because you never have a straight line. You have little small structures. Then you cannot define it. Now, Sohan may do this job. Like, don't fall in the trap of a fractal rabbit, as there is very open the definition. There are people that consider something as fractal, others may say this is not a fractal, but I mean, this is the most general definition we can have.
Okay, as you mentioned, let me just tell it. So that joke came is at the time of formation of the fractal when this research was going on. So a rabbit is a three-dimensional body. But if you really go through its tail and leg and all this on the periphery, then you will find out a fractal dimension 2 point something. So when the formation of fractal, then people ask that what will be the dimension of a rabbit, and it's like 2.6, 2.7. So it really depends on how you are measuring.
Mm.
So that's why this joke came, that don't fall in the trap of fractal rabbit.
Yeah, so we will like decrease this definition along the talk and say what this is like a bit polemic. Now, first, Excel says similar fractals. We have, for example, the Yadik-Koch curve. For example, we start with a straight line to make this fractal. We start with a straight line, then we break this in three, and we put here like a third and here a third. And we repeat this pattern with the straight lines until you have like something very with lots of peaks. We have this example for the continuous fractal and two examples for the discontinuous fractals. The Cantor set, you start with a solid line, then you also divide in three, remove the middle, and repeat this until you have like a dust of masses with this pattern. in higher dimension sponge that is like this one. So you remove the cube in the faces and at the middle of the cube, and you repeat this in all the small cubes. These are the exact examples of the self-similar fractals. And one direction one can take when it's thinking of the time in this kind of discontinuous fractals is like characterize their mass. So if you have a cube with certain length L of his sides, then the mass will goes as L with a power 3. But if you remove the mass, if you have a fractal, then you can say that its mass goes as a power law, but with a fractal dimension beta. Beta is a non-integer number. Well, now what is the notion that we can have when we have like something similar for continuous fractals? Now, for example, you have a line, you divide it in 2, the number of lines you will have is 2, you divide a line in 3, the number of lines you will have is 3. And you do this also for squares, then in those cases, you can see more like the pattern. If you divide by half one side, you will have 4 squares. If you divide by 3 one side, you will have 9 squares. This is like 2 at power. It is like 1 over s at power what you like of the dimension. Yeah. So this is an example of self-similarity. You have a cube made of cubes, but this is not a fractal. Now, from this relation, we can get D and use this for the case when we have fractals. This is clear because yes?
I have a question. So, at the beginning, you were showing the map and the terrain or the shore between the water and the ground. We will see kind of fractal structures. But in this case, we have a really specific mathematical rules for building them, which is not what happens in fractals we see in nature, right?
An example of this. There are examples of fractals that are more like things you find in nature. There is called snowflake. And so it's just like a triangle, and then you put triangles on the...
No, what he is asking that if your formula for finding out the dimension remains same for the natural fractal.
This formula is just for exact self-similar fractals, and then we will see a more robust thing.
Because in the definitions, no, the definitions agree in both.
Yeah, definition remains same, and then you can give a different kind of transformation to this definition, but the basic definition is this.
Yeah.
I mean, the question is, to me, it's not so clear how to apply this scheme to objects you don't know, right? In fact, I mean, you divide, so to say, where do you start, or how do you divide your set or your object?
By equal parts.
End, right?
Yes, by equal parts. So you define length S, and S completely cover your. Yes, it's like dividing the integer by 2, 3, 4, and so on.
But I could divide, for instance, for 2 dimensions, I could divide the square into 2 rectangles.
No, they have to be squares.
But if you have an arbitrary fractal, you don't know what they have to be. This is my, this is.
So right now I am like in the.
Just one. Oh, okay, so.
So I am characterizing with a unique length my shape, then I need right now squares. Then.
I think maybe you want to describe the normal dimensions
Yes,
as your points, and then you want somehow to interpolate.
And these have to be basically your basic building block have to be regular. That's the main one.
Yes.
So it could be a circle, for example.
Yeah, sure.
But you cannot take a rectangular because it is not uniform in that sense.
So it's just it's more a motivation, it's not a definition.
Yes. Yes, just to explain the self-similarity. Exact self-similarity. Well, now, for the counter set, for example, we have the solid line we used to have, and we divide it in 3, and then it's like we are here, and we remove the middle. Then S is equal to 1/3, and we have just 2 masses. And this will give us the fractal dimension. If we make more iterations, the fractal dimension will be the same. Now for the Koch curve, is again like we start with a solid line that we divide in 3, then our division is 1/3, and the number of lines we have is 4, then this is our dimension. So one has to see that this dimension is bigger than 1 because it doesn't live like in a line, and those are smaller than 0 because it's less massive than a line. It's smaller than 1, sorry.
So following that rule, can you have a fractal dimension bigger than 3?
Yes, if you are in a higher space.
Okay. So for example, the fractal dimension of that cube is less than 3.
Yes. And this is from the point of view of the math definition. Okay.
¿Puedes repetir la definición de la masa?
Que si tú tienes un fractal, la masa sigue una ley de potencia con la longitud lineal de tu fractal. Pero beta ahora para un fractal va a ser menor que tu dimensión de tu figura original.
¿Para qué la beta entonces?
Beta es la dimensión fractal.
O sea, beta lo vas a estimar, ¿no?
Sí.
Tampoco no me quedó claro n de L, o sea, tienes el fractal, te doy una L, entonces tú me das la n, ¿no? Evalúas la masa dentro de algo que tiene el tamaño de L.
Ok.
Pero de qué, o no importa, puedes tomar la L en donde sea.
No, una forma.
Ahí si no es fractal, beta es 3, ¿no? Y es el volumen de esa cosa.
Sí, pero puedes, ¿cómo programas, por decir, la función que te da la n?
Por la densidad.
¿Cómo?
How do you make a function, say, on the computer, that the input is L and the output would be M.
Yeah, because you have a, how can I say, you have an irregular structure.
Don't say because, just tell me how.
How you do that?
Yes, how you do that exactly.
So a way to see it is like
You just form the
the,
structure and then you can start increasing the size. And your density have to be uniform, that's it.
the way to see a relation between those things is that you always have a length L, but you are changing your unit of L. So
Change
now
the value of L.
Value of L, yes.
your
I mean, you
so
like a
L is this, but here L is defined in a discrete space to better understand it, and your unit is of the same size of L. And here, just to like not change your where is confined your fractal.
You write down the function, M of L. And so what is the domain of this function? The possible values of L, they are arbitrary, right? Well, they should be positive real numbers.
Yes.
And what you give back is also a positive real number.
Yes.
So you have your fractal, and I can give you a value for L, and then you must give me a value for M.
Yes.
And I just want to know how you do that. How do you compute that number? And you cannot say this L is related to that, and then it is this. No, I give you the L, right? You don't have it, right? It's arbitrary.
Yes.
Okay, so if you have the mass, you just can,
Right.
and you have
I
L.
don't have the mass. I only
Okay.
have the fractal.
You need three things, right? The L, the beta.
No, the beta
No.
also don't have.
No, it's a simple thing.
You
Okay,
can calculate.
It's a simple thing. You have a fractal structure or program in your computer. You put an L, so that's your input, and you get an M.
How do you get that M? That's what I
Because if you want to form, for example, if you want to form a merger sponge, so you will have a three-dimensional lattice. And in the three-dimensional lattice, if you have a specific structure in your three-dimensional lattice, which spaces will have mass and which spaces are not. And then you just keep increasing your value of L.
increase.
Or decreasing or whatever.
You can't, because this has a maximum dimension 1.
Which one?
The sponge.
Yeah, when you think of, but this is just for you maybe.
Or
When you
can
think in terms of
well, the
process
counter said you
forming
also cannot
fractals,
simply increase it. Right?
Yeah, why not?
so
I can see
you
how you increase it. I mean, you have to explain how to increase it.
So you have a one-dimensional line, right? Okay, which you start with a one-dimensional line. Now, following that scheme, you form the Cantor set.
Yeah, you get to smaller and smaller and smaller scales, but not to larger scales.
you
Yes,
can
but
do
there's a
it in
formation.
both
Now your
ways.
whole fractal structure, the whole line, that's of size L. Now, in fact, that's my variable. Now in my computer, I put the another size, which is to increase your size of lattice, and you have the same structure.
Maybe it's
inside.
1.5.
1.5 what? L, value of L. Yeah, it doesn't matter. If it's a continuous space, it doesn't matter.
But then what you are doing with it, I don't get it. I mean,
So if for a given M, L, you have a given M. Okay, in your computer is how many
now you
points?
don't have a given M, you have to calculate that M.
That's what I'm saying. If given L, you have a M. You can get an M.
Because you have to compute it.
Yeah, sure.
Can you give me the merger spot?
Maybe I don't know.
So here we have, let's call it a true set. You have
So what
your
is
base
this
unit.
then?
You have your
L,
base
that's
unit.
L.
No, this has a value. It's not L.
Yes, that's it. These are a value. Okay, fine.
So it's 1.
Okay,
Now I give you a value 0.5.
okay.
What you're doing.
No, can I try
Yeah.
to? So let's say our base unit would be 1. This would be our base unit. And because it's a fractal and it's self-similar, we want to fill the whole space with the fractal made with this unit. And we're not going to need 9 of them to fill the sponge. We're only going to need 12.
12.
Yes. So the mass is not going to increase with the cube.
You need 12 what?
Not 12, I'm sorry. 12 of these units. So the mass is not going to increase by 27.
So
It's going to increase by 27 minus 5. So that would be 22. Yes, because this is going to be our unit. We don't need 27 of these to make the bigger one. And this bigger one,
okay, yeah.
Yeah.
What do you do with the Koch curve?
the
You
same.
want it to
Same.
make it larger,
We can make it smaller
but you cannot make
and
it
fit
larger.
it 4 times.
You can make it smaller.
If that's the point where same self-similarity comes. If you want to make it larger, you will just repeat the same process, self-similar way. That's the word. That's where the self-similarity comes. Could you go back one slide before?
I mean, this is what worries me, right? Because you have your
No.
You have your-
Just look at this is quadratic construct. Okay. So it will have the if I just draw a bigger one, it will have the exactly same structure repeated.
So this is this, this is this, this is this, this is this.
So if I want to take a larger one, it will
And then-
keep repeating itself. So you can keep increasing.
But you really stretch it then.
No. Self-similar. You take
Okay. Oh, okay.
self-similarity. That's exactly where the self-similarity comes. So your dimension never change.
Okay, you can double it, right? But still, no, if
You can make it any times because these building blocks are tends to 0. The size of the building blocks tends to 0 for the definition of the fractal. So you can make it any time. 1.7 times if you want. Doesn't matter.
and some square root 2 times.
Yes. Yeah, that I don't know. Square root 2 times because it
I
should
mean,
be.
it's eventually
It should-
very
it should-
complicated. Right? Well, not complicated, but impractical. So.
Yes. If you have an irrational number. But if you have a rational number, you can make it any time.
And you should know beforehand what is this type of self-similarity for that to work.
Yes, because there are two parts of the fractal.
So-
One is the formation of the fractal and is the measurement of the fractal.
Yeah, but maybe you don't know how the fractal is formed. Let's
Doesn't matter. If you want to measure
say
it.
the chaotic cycle of a dimension.
Yes. It doesn't matter. If you have a stochastic fractal or a chaotic fractal, then you just follow the formalism of measurement and you will get a fractal dimension. And in that case, you really exactly do not know how the fractal structure is, but what you know is what is the fractal dimension. And its different characteristics.
How do you?
I think
That's
we
what
should
you want to
continue to
calculate.
the following.
Okay, maybe we should stop
Because-
here.
Because until now, he is talking about mostly the formation.
Yeah, and exact self-similarity. Now, the most used method for measuring the fractal dimension on real objects is the box counting method. This consists in put an edge over your fractal, and then you count on how many of these squares is your fractal. So for example, here just the contour of the S1 is forming the fractal. You count how many boxes, and those boxes will follow a power law with the fractal dimension df as you reduce the size of the box S. And well, this follows a power law because of the self-similarity. And there is another definition similar, that is that you discard the empty boxes and then MS is the average number of segment or mass in a box of length S. This definition is more like for calculations. Now, this is very used, but it's not like the most strict fractal dimension you can take from a real fractal. The most strict is the Hausdorff dimension, and this consists in you try to cover with figures that have certain characteristic length. your fractal. Now, you can cover it with lines, you can cover it with circles, or with spheres, or something with higher dimension. So, okay. Now, the sum of these, did you cover with many of these figures? And this should give you like the perimeter of your fractal. Then you search for the smaller path you can take for covering it. And once you find it, you make the limit of your radii tends to 0. So here epsilon is the diameter of the circle. Okay, questions here?
What do you mean with the topological dimension?
Okay, so just like a table to use right now, the topological dimension of this perimeter should be 1. The topological dimension of a point is 0. Topological dimension of a plane is 2. Of a cube is 3. Okay.
So for example, here in this picture, your Euclidean dimension is 2. Okay, it's a 2-dimensional body.
Yes.
Now, if you really go through this, with a continuous line, if you go through this perimeter, then it's just one line. So that's the topology is just in one dimension. So then your topological dimension here for this body is like 1. Now, if you really want to do the fractal dimension, then you have to follow this formalism where you actually have to fill it with 2-dimensional bodies, and now you have to make this dimension of the size of this 2-dimensional body smaller and smaller, and then you make this formula which will give you the dimension of the fractal dimension.
Okay, yeah. So we'll go to this. If you try to cover the perimeter of the island with lines, you never will be able to do it because this is infinitely small. And this will diverge. Now, if you try to cover it with the amount of contour that is inside your area will be too small, such that this measure in the limit will tend to 0. Way to visualize this more mathematical, but still like not so strict. We saw before that the number of spheres, and before was squares, but then also can be the number of spheres covering, will go as this, using the box counting method. And then if all the spheres are of the same size, more or less, we have this number of spheres with this radii. Then we solve the sum. Okay? And we have this measurement will be more or less like this. And well, as the R tends to 0, we will have two limits. If D is smaller than the fractal dimension, then the measurement tends to infinite. If D is bigger than the Hausdorff dimension, the measure tends to 0. And there is a transition, and it's the one that gives us the Hausdorff dimension between 0 to infinite. Now, the Hausdorff dimension is bigger than the topological dimension. This can be seen like in every examples. For example, for the Cantor set, you have thus, topology dimension is 0, and the Hausdorff dimension is bigger. For this Coloquio curve, the dimension was around 1.2, and the topological dimension is 1. Also, these figures live like in a bigger
So
place.
for the Cantor set, the topological dimension
0.6.
Is
For topological dimension.
is zero
0.
because you repeat this until you have a dust.
Yeah, it should be 0.
Basically, for the fractal dimension, for Hausdorff dimension, your building block of the measurement should be discrete. That's an important part.
No,
Why not?
for the Hauser dimension is not.
No, for your building blocks,
Yeah, the building blocks.
that
Are,
have to be discrete.
yes.
Otherwise,
No, sorry. You can apply the Hauser for a discontinuous fractal because the criteria is just that you need to cover the fractal. Then if you have spaces, you just will do things like this.
but this measurement block,
And the sum
have
of
to
the
be discrete.
radius needs to be the minimum.
yes.
Okay. Well, this is the most complicated. More questions? No? Now,
Can
When-
you have one question
yeah.
about the dust? Does it imply countability? So is dust countable or it is not countable?
So these terms are not so familiar for me, but it should be uncountable.
At least the Cantor set is uncountable.
Yes.
Yeah, that's somehow my problem with dust.
Because
I
you
don't
can
think
have
that it's a
countable things, but tends to infinite, and it's still are countable.
What?
You can have a countable set of things, but and be infinite. As I know, you can. So I am not so familiar with the. I
No,
just
there are
read this.
infinite sets which are uncountable, and there are infinite sets which are not countable. And the Cantor set, because it consists of, you may say it consists of compact intervals, closed intervals. It's not necessarily uncountable. I would guess. Yeah, no, I'm not sure. I think, and well, there are sets which have measure 0 and are uncountable. That might have to do with the dimension, topological dimension.
Yeah, so you did a question, and I found it in a book. But
So I just wanted to know
will
what
not
means
feel
dust
still. Okay.
in this sense.
Well, when you have like mass points forming a fractal or discrete things forming a fractal, you take like another path and you can do measurements like the 2-point correlation function. And this is the probability that a site will have a unit mass. Given that a certain distance r, there is another mass. Now, this 2-point correlation.
Okay, I'm sorry. Cantor set should be uncountable, right? Because if you keep repeating the process until it becomes a dust, so the number of points are with the interval between 0 to 1. Okay, when you didn't start the process, the number of points of the whole line should be same as the number of points once you reach the dust. So it should be uncountable. For the Cantor dust, it should be uncountable from that logic. And that's why the dimension goes to 0. Topological dimension.
No. I mean, countable set of points also have dimensions.
Oh yes, that can happen.
Yes, the Cantor set is uncountable.
Okay. So this two-point correlation is very cool because usually you have like a rest here of the averages. This doesn't have it because suppose you have a mass and a certain distance you don't have any mass, but you are resting here the average. So you will add like some information of mass to your measure. So this two-point correlation goes from 0 to 1, this in between. And well, rho are the possibilities of having mass is rho equal to 1 and rho is equal to 0 for empty sites. And so for an infinite fractal, you will have only this behavior on the two-point correlation. And it follows a power law with exponent minus alpha. Now, one can relate this exponent alpha with the post-counting method, but the relation that is only true when you have a monofractal. So what this integral says is you have a box, and then you sum the probabilities of having particles that are at a distance smaller than this box. And this is known as the correlation dimension that for monofractals is same than the measurement you get from the box content and cost of. Then, well, we have a very simple integral here. You get this. And this integral one dimension, then if you make for the other dimensions, you will get this. And we have a relation with two-point correlation and the fractal dimension. Now, you can also get the fractal dimension through the distribution of the distances between your objects forming the fractal. I call this D, L is the distance. This will follow a power law that decay with exponent K and is related with the fractal dimension by this. This can be proved through the two-point correlation, but I don't have to prove right now, so maybe for later. And something interesting here is that you study the distances between your fractal points. But even if you study the distance between the fractal points, if you have a D term, and it is because you search like in every direction for mass. And well, D is the Euclidean dimension. Now, what we can do with this, we can use this not only for measure the fractal dimension, but also for building a fractal. Now, if we suppose this equal to 1, then case this, and we have that the distribution of the distances is like a Levy flight. So this is the alpha of the Levy flight, not of the two-point correlation. So if we put points and we take distances from the Levy distribution, we can in this way build a fractal.
Okay, well, here I have that comment, right? So the way you define that, by definition, you have a countable set of points. Fractal is a countable set of points. Then the Hausdorff dimension is always 0. It cannot be a fractal.
Well, you make this tends to infinite.
Doesn't matter.
Doesn't matter.
It's infinity, but it's in any case, the Hausdorff dimension, you can check it for a countable set of points is 0.
I don't know how.
And it's precise, this is precisely a case which I didn't know, where the Hausdorff dimension and the box counting dimension are different. So the box counting dimension may be non-zero.
Yeah.
But there are, it's for me also.
Yes,
it's a problem that the countable set could be a fractal. For me, it's strange.
Yes, that part you are right. For example, we can say the Hausdorff dimension and the box counting dimension are similar, but they are exactly same for the uncountable sets. But for the countable set, the Hausdorff dimension goes to 0 at the box counting dimension.
I don't know. I mean, that we should check with a lot of care. It's not, I mean, yeah, it might be a hypothesis. If you have sets where the box counting dimension gives you 0, gives you a finite value, and Hausdorff dimension gives you 0, there might be very well sets where the two measures give different non-zero numbers. Why not?
Why?
Why not? The question is why not? No, you have to prove it. It's not, it might be true, but you have to check. It's not obvious.
So the power law distribution diverges.
By
don't know if this
definition, your
can-
power law okay. In that sense, your power law distribution that also should exist in an infinite line. If your power law distribution do not have any characteristic length scale, because it's polar, it's divergent one, right? So if you do your simulation in a finite space, okay, where your distance between interparticle distances goes as a power law, that by definition, that power law definition is not valid for a finite space because it's diverging.
Of course, you can diverge in many different aspects, right? So, for instance, take the Cantor set. Now you would expect, I mean, after this, you would somehow expect that the two-point correlation function has a power law.
Also could
For a Cantor
have
set.
something to see with the
But
scale
of course, you have to
free.
go ever smaller.
Yes.
So it doesn't matter if you make a finite object and go to ever smaller scales, or if you have a fixed scale and blow it up. In principle, it doesn't matter.
Yes.
But the way this is constructed, because you have talking about isolated points, then by definition countable. I mean, say you could take the Cantor set again and only keep the endpoints of intervals.
Okay, so that's what Thomas Hernandez.
Then it
Has
becomes
a
countable again. And you could ask if this is a fractal or not. But it has Hausdorff dimension 0.
Why?
Because it's a countable set. Because it's countable. And of course, I mean, one would have to prove it, right? You would have to take the definition of the Hausdorff dimension and check what you get. But there will be a point where using Hausdorff or using box counting dimension.
No, for a finite system, says the way. Please go back.
We are talking about infinites, of course.
You're talking about the infinite system.
Yeah, and what you have to do in the definition is this, just as it is written, right? You cannot do any finite approximation to that. It's not the point.
Okay.
But because the construction is so simple, you can find an answer to this.
Yes, that I agree, but yeah, it's similar but not same. But that's why the box counting dimension are for the finite space.
No, also they work for infinite space, and
Yeah, but it works for the finite space.
you only have to you can build your proof on box counting. It's still a mathematically rigorous proof. It's not just doing numerics.
No, I don't understand what you are saying.
For the Cantor set, you can do box counting
Yes.
up to infinity. I mean, literally. I mean, in the form of a mathematical proof. By induction, by whatever.
Mm-hmm.
And then you can see the difference between Hausdorff dimension and box counting dimension.
Why that will be different? That's what I don't understand.
Well, if you only take the endpoints of the intervals so that you get a countable set, then the Hausdorff dimension must give 0, and the box counting dimension will not give 0.
Are you going with the scale-free?
And probably it has to do with in the power laws. In any way, there are a lot of counterexamples.
No, my point is that the power laws distribution or this correlation or whatever you say, that's scale free. So if it's free, then your dimension should not change if it's countable or uncountable.
Well, it could be 0, and then it will not change.
No, it will not be 0. Any value of the dimension, it will not be different. Because by the definition of scale free.
Well, that I don't know. Let's discuss this. We have a session for discussing that.
Yeah.
So let's do it.
So now we go to multifractals. Multifractals can be seen, multifractals are defined in papers and everywhere by the measurements. But if you make like a physical description of it, it just can be seen like overlap monofractals that are correlated or fractals made of fractals. And now it will be more clear maybe later. So examples in turbulence is where you will find most of bibliography of multifractals. And the dissipation of energy that occur in turbulence is forming a fractal. Also on phase spaces of some chaotic systems, and you can find multifractals and are used for study financial markets. Just like examples of where are applied. Now, how to build a multifractal? This is more essential. So now you play with the mass of the fractal. You start with a solid line, and you define some weights, such that your weights sum up 1, and one of the weight is smaller than the other, such that you create like the composition on the mass. And well, you divided your lattice, and then you put those weights and repeat this process. So from here, this next iteration is here, and then you reach like something like this. Then one way of see the multifractality is like the masses that are equal are forming a fractal, and the masses that like are equal but bigger are forming another fractal, and so on. Another example is the Cantor set, the multifractal Cantor set, that is made very similar to this one. Just imagine you have here a space. And so you have a line, then you divide in 3, and you multiply the mass here. You divide again, and here the mass is multiplied, and here is the double than this, and so on. How we characterize a multifractal? As we have very monofractals overlap, then what we make is like highlight certain structures by amplifying with a parameter Q. So we divide our fractal in boxes. Now, the mass on each box is elevated a power Q. Here we have the normalized mass, a power Q, and it will go as a power law with the window size with exponent Q minus 1, and dq will be our dimension that for the fractal that we highlight for certain Q. So dq is called general dimension. As we saw before, the correlation dimension should be for q equal to. The box counting dimension is for q equals 0. And these are the empty boxes, such that when you consider q equals 0, you don't have like masses in empty boxes. And well, this is the mathematical way to write the general dimension when the window size tends to 0. But see, you can get it from here. Now, other way of visualize the fractals, as we saw before, is that you go to a very, very small scale such that you only see monofractals in your lattice. A very ideal small scale. And then you have repetitively certain fractals, and this repetition is made in such a way that those repeated fractals create another fractal. Hence, you have fractals of monofractals. So the monofractals will be characterized by the dimension alpha, and we call it local dimension. One can only measure the expected value of alpha because of these ideal suppositions. And the fractal dimension of the fractal made of fractals is f alpha. Now, we only can measure the expected value, and how we do this. We define the probability of having certain mass in a box, the probability of selecting a box after elevating the masses at power q. And then this is how it should look like each alpha, but we only can measure the expected value after elevating the masses at power q. Hence, we measured the expected value of alpha I from the probability distribution mu q. This is clear? Okay, so you have many alpha i's, but the expected value of mu q is the one that will tell you which alpha I take.
Mu Q? What did you say? Mu of Q.
Yes.
In fact, I got lost when you started to talk about expected values because there is no probability theory behind it. In which sense?
So the probability.
Maybe you can go one page back, one slide.
No, I just didn't put the equation, but here is mi and 0 and mu q mu I.
So you have a deterministic process which produces this fractal, right? Where now the masses change. They're no longer uniform.
Yeah.
And then,
And then you try to characterize them.
sorry?
You try to characterize them.
Okay, yeah, right. And then you're analyzing powers of mass ratios instead of just if all masses would be even, then these powers would always be zero or some constant, or exactly the same constant, right?
Yes.
Can you go just make, I think, one page before? Yeah, here. Right? So, for instance, if we just would go back to the old Cantor set without changing masses, then mi over m0 would always be the same.
Yes, for Q0.
And you could say it is 1 or 0, and then the q would not matter.
Yes,
There was no point of defining the dq.
yes,
But now the masses, you have different values for this ratio, and then the q matters.
yes.
That's why you're interested in this dimension, which depends on q. Until that point, I understood. But then I got it.
So, okay, so we have the idea that we can have monofractals that form fractals at a bigger scale. And the fractals,
Why? Okay.
because you have,
So this is a different construction than the one you presented, or it is just a different form?
it's a different form of point of view, but those things are connected by a Legend transform, and now
Why?
a Legend transform,
Legend transition.
and it's the following slide.
Well, maybe we should talk about that after the
Okay.
Okay, so
but I
just,
think it's a good point to stop. So you came to with these masses which are different.
I almost finished, and
This is nice for the introduction.
this is just out the concept, so we can finish here if.
you have just one more slide.
So it's just the Legend transform to connect the general dimension with alpha and alpha. So it's.
So,
I just have one comment about multi-fractal because when you are